Today I am describing about performance of digital modulation over wireless channels. Firstly, I introduce what is modulation. Modulation is a process of suppressing low frequency information signal on a high frequency carrier signal. There are two types of modulation. First one is analog modulation. In this type, parameter of the carrier is continuous in accordance to the input analog signal. Second one is digital modulation. In this type, parameter of the carrier is discrete. Digital modulation can be considered as digital to analog and the corresponding demodulation as analog to digital conversion. There are three types of digital modulation: ASK, FSK and PSK. In digital communication, the modulating wave consists of binary data and the carrier is sinusoidal wave. In this diagram, this is the baseband digital message signal and this one is analog sinusoidal carrier signal. Now in ASK, bit 1 is transmitted by a signal of one particular amplitude. To transmit 0 bit, we change the amplitude keeping the frequency constant. Now in FSK, one particular frequency for 1 and another frequency for 0. In PSK, one phase change encodes 0 while another phase change encodes 1. To transmit 0, we shift the phase of the sinusoidal by 180 degree. Now, bit error rate. It is an quality measure of digital signal. In telecommunication transmission, the bit error rate is the percentage of bits that have errors relative to the total number of bits received in a transmission. Basically, it has been altered due to noise, interference, distortion, or bit synchronization errors. In an AWGN channel, this is the modulated signal. It has a noise n of t, which is a white Gaussian random noise. So basically, its mean is 0 and power spectral density is n naught by 2. This is the received signal. For calculating the SNR, we have to find received signal power PR and power of noise within the bandwidth of the S of t. PR is determined by transmitted power and the path loss, shadowing, etc. And the power of noise within the bandwidth is N naught B here, because uniform PSD is N naught by 2 over 2B bandwidth. So the received SNR is PR by N naught by B. SNR is expressed in terms of signal energy per bit, which is known as EB, and energy per symbol, which is denoted by ES. Here TS is symbol time and TB is the bit time. For performance analysis, we are interested in the bit error probability, which is PB, as a function of gamma B, which is SNR per bit. Firstly, I considered here BPSK modulation, which is binary phase shift keying modulation, with coherent detection and perfect recovery of the carrier frequency and phase. In binary modulation, symbol corresponds to one bit, so the symbol and bit error rate are same. This transmitted signal for sending a 0 bit and this one is for send a 1 bit. We know probability of error is this one. Firstly, we calculate d minimum. After that, bit error probability, which is PB, can be simplified using Q function. Now, QPSK modulation consists of two BPSK modulation on in phase and quadrature component of the figure. This is the constellation diagram of QPSK. It is a representation of signal modulated by a digital modulation scheme. It is useful in showing the phase of PSK modulation. Bit error rate of each branch is the same of as BPSK. Regarding to figure condition, the symbol 0 is sent and the probability of error is bounded by the sum of probability of 0 to 1, 0 to 2 and 0 to 3. We can write like this. Using the approximation of Q function, we can find the symbol error probability here. For MPSK, which is signaling, we can easily calculate the symbol error rate approximation. By using the MPSK constellation diagram, the symbol error probability can be calculated. Approximation of symbol error probability is only good for high SNR here. The SER for a rectangular MQAM with size L is equal to M square can be calculated by considering two MPAM on in phase and quadrature components. This is the diagram of QAM constellation. The error probability of QAM symbol is obtained by the error probability of each branch and is given by this one. If we use nearest neighbor approximation for an MQAM rectangular constellation, there are four nearest neighbors with distance d minimum. Now, in order to calculate mean energy per transmitted symbol, it can be like that. A fading channel can be considered as an AWGN with a variable gain. The gain itself is considered as a random variable with a given PDF. There are three different criteria that can be used to characterize the random variable PS. The first one is the outage probability Pout, defined as the probability that gamma is false below a given value corresponding to the minimum allowable PS. Second one is the average error probability PS bar, which is averaged over the distribution of gamma S. Third one is combined average error probability and outage, defined as the average error probability that can be achieved some percentage of time or some percentage of spatial location. Now, outage probability. Outage probability is the point at which the receiver power value falls below the threshold. It is relative to gamma naught. Gamma naught specifies the minimum SNR required for acceptable performance. For example, if we considered digitized voice, PB is equal to 10 to the power minus 3 is an acceptable error rate since it generally can't be detected by the human ear. Thus, for a BPSK signal in relay fading, gamma B is less than 7 dB. So it would be declared an outage. So we set gamma naught is equal to 7 dB. In relay fading, the outage probability become this one, and the required average SNR gamma S bar is this one. The average probability of error is used as a performance metric when TS approximately equal to TC. We can assume that gamma S is roughly constant over a symbol time. Then the average probability of error is computed by integrating the error probability in AWGN over the fading distribution. Here, PS gamma is the probability of symbol error in AWGN with SNR gamma. We can compute probability of symbol error by making the change of variable. In relay fading, the received signal amplitude R has the relay distribution is this one. The SNR per symbol for a given amplitude R is this one. Now, after differentiating and put the values in the above equation, we find average SNR per symbol. Now, this one is the average probability of error for BPSK in relay fading. Here, approximation holds for large average SNR per bit. This one is for binary FSK and this one is for DPSK. It is interesting to compare bit error probability of the different modulation schemes in AWGN and fading. For binary PSK, FSK and DPSK, the bit error probability in AWGN decreases exponentially with increasing gamma B. However, in fading, the bit error probability for all the modulation types decreases just linearly with increasing gamma B bar. Similar behavior occurs for non-binary modulation also. Thus, the power necessary to maintain a given PB, particularly for small value, is such higher in fading channel than in AWGN channel. This is the reference where I take this all stuffs in this presentation. Thank you so much.